Okay, hey, welcome here. I thought I would do number 55 because after I just finished 44 and made a big deal about getting the charge inside, a number of people were asking me, well, can you show that? And this is it. And this is actually the one I forgot. When I was doing the other one, I pointed out that you needed to be careful on 57 and I was thinking there was a second one, and this is it. This is the second one here. So, chapter 24, number 55. It says this. It says we had a solid insulating sphere of radius r, and it has a non-uniform charge density. So maybe here is the sphere that is charged, and it says here a charge density that varies with r according to this expression. Density is a r squared, where a is just some constant. They don't really say what it is. But what that would mean then, if I were kind of drawing a picture, is the charge would be kind of weak here and get bigger and bigger and bigger and bigger. In fact, it's a quadratic. So most of the charge really is on the outer parts of this. If this was, say, the Earth, I would have to say most of the charge is on the crust of the Earth, and very little charge is in the core of the Earth, because equation that is quadratic does that. And so the charge the charge density is much greater out here, and the volume is much greater out here. So you put those two together, and most of the charge is really far out here. Very little bit of it is actually inside. But the real key to remember here is it's a non-uniform charge density, okay? It says, A, show that the magnitude of the electric field outside the sphere. All right, so let's start there, is given by this equation. So let's go outside, and I'll do my Gaussian surface in red here. And so I'm going to put a Gaussian surface here. And I will begin with Gauss's law. And so the integral over the electric field over the surface, some surface area, Gaussian surface. So this flux calculation is equal to the charge inside over epsilon naught. Okay. And again, this is where these lines of symmetries become real important. If I drew a line there or a line there, those would all be a line of symmetry. That is, if you took the charge and you flipped it, you'd get the same thing. And so that means you must have an electric field, like this pen here, pointing in a particular direction. So when you flip it, it's still in that same direction. An electric field pointing this way means if you take that charge and flip it, now the electric field's pointing in a different direction, and yet you have the same charge distribution, so that's impossible. So that's why you have to be able to flip it, and it has to be pointing in such a way that when you flip it, it's still pointing in that same way, because we're still getting the same charge distribution. And that can only be true for lines of symmetry. So that's our argument of why we pull that out in front. We get a dA. It's also our argument why we keep saying that angle must be 0 when you take that the dot product, which is why then this side of the equation becomes something like that, where we just have the electric field pulled out because it's a constant, and then the surface area, and that's the 4 pi r squared. And probably the harder one for this is right here, is the charge enclosed. And I'll just tie this together with the last problem I did, which was, 44. And I just said, look, anytime you have a spherically symmetric distribution, And we did. We had an insulator then surrounded with a little air first, and then a conducting shell, and then more air. And so all of that was spherically symmetric. And so we got this equation for every region, A, B, and C, and D, back on 44. And we get it here too. But of course, then the trickier part then for A and for B is, what is the charge on the inside? And so this is that fancy integral I want to be careful with. Let me just leave this alone for a moment and say, okay, charge inside. This would be adding up all the charge. So if I come back over here to my Gaussian surface, this would be saying take chunks of charge, and I'll do them in little shells, spherical shells. And of course, this case, I'll just add up the shells till I get the edge of the charge. I don't need to go all the way out to the Gaussian surface. As a matter of fact, that'd be a mistake if I did, because there's no more charges to add up. So keeping that in mind, and together with the fact that the definition of charge density is the charge per volume, we can then do a substitution of dq with rho dV. And in this case, if we were to pull the density out in front, we would be getting this equation, which would be a mistake, because the density is non-uniform. That's why I'll say it again. Taking Q equals to rho V is true only when you have a uniform or constant density. And so we use this quite a bit, and I did use it in 44, but pointed out that you can't always use it, and this is an example of that. So this would all be wrong. So let me just keep going in this direction. So to answer the charge inside, we would have to put the equation, which is back here at the top, for the density, which is A times R squared. And then if we were adding up these shells, these volumes, and maybe this is worth looking at. I was trying to visualize this to a few people who were in the Zoom help session on Friday. I grabbed a spherical object. Closest one I have is this Dodger baseball here. But if I grab a sticky note here, and you wanted to know the volume of a shell, so imagine me wrapping this sphere with some aluminum foil, or in this case, I'm just going to wrap it with a piece of paper. I know my paper is not big enough to wrap the whole thing, but if I wrapped it all the way around and then unfolded it, and I asked yourself, what is the volume of this aluminum foil or this paper wrapped around this sphere? I would say it is the area of this piece of paper times its thickness. Now, the area would be the surface area of the shell of the sphere. So that would be the 4 pi r squared. And the thickness of it, thinking in terms of calculus, the thickness of one of these things would be this dr. And so that's how I transfer this dV into a dr. And again, maybe I can use a fancy word like I did in 44. You see, when I changed it from a dq to a dV, there's a mathematical relationship between them. That mathematical relationship is called the Jacobian. So I can change it from this variable from a dq to a dV. And I'm going to be doing the same thing. I'm going to change it from a dV variable to a dr. And so basically I'm saying this, that dV, a little bit of volume, is the surface area, 4 pi r squared times the thickness. So this is the mathematical relationship between a dV and a dr, so this is the Jacobian. All right, so we did our first transformation of variables from a dq to a dV, and we got this rho. which we then substituted in its equation. Then we did another change of variables from the dv to the dr, and that's the second Jacobian. All right, well, maybe I need to go to another piece of paper. Maybe I better label that as 1 in case I need to come back to it. Maybe I'll even bring it close by so you can kind of see it there on the camera. Okay, but what I now have is the charge inside is equal to this integral, which I'll simplify. For example, the a is a constant. I'll pull it out, and I'll put the r's together. That's r to the 4th, and I'm left with a 4 pi, which I probably should have pulled that out in front. I'll do that on the next step, and then the dr. And so then this is an a of 4 pi, and then I have this integral, which isn't a too hard of integral to do, so I'll do it real quickly here, but I should talk about the limits again. And so coming back to here, we're going to add up these chunks of charges. Remember, it started down here with this idea of adding up these chunks of charges, and we're going to add them up from where? Well, starting the center, and so r is 0, and get bigger and bigger and bigger and bigger and bigger until we get to, in this case, capital R. Let me just check. Do they say, yeah, the sphere has a radius of capital R. So we're not going to go all the way to the Gaussian surface. The reason being is we don't have any charges beyond there. And I realize Gauss's law says, what is the charge enclosed within the Gaussian surface? And because it says it that way, you might be tempted to add up all the way to the Gaussian surface. And I suppose you might even say technically you are. It's just from capital R onward, there is no charge to add up. So we just go to capital R. And so we need to set up our bounds of our integral as 0 to capital R. So when we integrate this and get r to the 5th over 5, it's evaluated from 0 to capital R. And so we get a 4 pi capital R to the 5th over 5. And so now we can come back to our earlier equation. Here it is. And saying the electric field is 1 over 4 pi epsilon naught times the charge inside. Oh, huh. Did I really do that back here? I apologize. 4 pi epsilon, this is supposed to be an r squared, shouldn't it? I wrote the epsilon twice, but that r squared not at all. And we like to put our constants together, so it should have been there. Okay. Oh, hopefully that didn't mess you up too much. Okay, so coming back to here then, the charge inside would be this a 4 pi capital R to the 5th, and I'm going to write it over 5, so I can then put r squared here. And then a few things simplify, the 4 pi being one of them. So it looks like in the top I have a capital A, I have a capital R to the 5th. That might be everything on the top. I've got a 5 on the bottom, I've got an epsilon naught on the bottom, and I've got an r squared. And I believe that's what they say to do. Show that the magnitude is, and they got an A, they got an r to the 5th, they got a 5, they got the permittivity of free space, and they got an r squared. Ah, perfect. Because then we can go on to B, and if all that made sense, hopefully it'll make B a little bit easy to see here. Because I would say B is, again, spherically symmetric, although this time they say show that the magnitude of the electric field on the inside is. But I would say, from the same logic, if we want to go back and rederive all of this, that if I were to draw a Gaussian surface in here, I would get that, and I would still get this. And so it's the same equation. And we're always going to get that equation when it is spherically symmetric. Now, that doesn't mean it's quite exactly the same problem, and here's the difference. Remember, this is the charge enclosed. And so if we come back to this integral back here, we said the charge inside was this integral. And for outside, we did not go to the edge of the Gaussian surface. What we did was the edge of the insulator. We just went to the insulator and stopped. That would be a mistake here in B because our Gaussian surface is smaller than capital R. So if this means the charge inside, we would only want to go up to the Gaussian surface and then stop, not all the way to the edge of the ball. And so here's the difference. The charge inside then would be A times an integral from 0 to R, little r, of 4 pi r to the 4th dr. So we get the 4, we get the A, we get the 4 pi, and we get the little r to the 5th over 5. And so it almost looks the same, but instead of a capital R, it's a lowercase r. So when we put that together with the 1 over 4 pi epsilon naught, and we put the charge inside, which is A 4 pi r to the 5th over this 5, and then divided by the r squared, we'll see that the 4 pi's, like up here, cancel off. But these r's are now the same and can begin to cancel. And so we don't have any capital R's, we just have lowercase r's to a power of 3. And then we still have our 5 and our epsilon naught. And so it's kind of like this back here, except these r's are really both lowercase r's, and that's why they cancel off and get you r to the cube, and everything else is the same. And I suppose I should check up here, show that it is a r cubed over 5 epsilon. Yeah, perfect. Good. Hopefully that's helpful.